class, this is your instructor James Quinn again, and I want to go over frequency distributions. What we're going to do is we're going to have some homework over frequency distributions, and this will be a two-part video because I'm going to go over the PowerPoint and then I'm going to provide you with an example of how to do the work. Then I'm going to go over how to solve your standard deviation variance formulas. I'll go over that step by step, but first I want to create this video for the PowerPoint. Well, when we're talking about frequency distributions, what we're able to do with frequency distributions, what we're doing is we're organizing our data. We're actually going to make some sense of raw data. And when I say raw data, I'm talking about numbers. So if you have a data set, it is raw data. It is unaltered. We haven't done anything to alter the data. It's kind of like if you are like a barbecuer or a chef or something like that. You have raw meat. You haven't altered that meat in any way yet. So that's what we're going to do with statistics, is we're going to take raw data and we're going to do some statistical procedures so we can actually organize this data and make sense of it. What is a frequency? What is frequency, and how a frequency distribution is created? That's what we're going to learn how to do. And I've seen a lot of videos on this. I've had other instructors, and I'm going to show you how to do it very easily. I think it's the easiest way to do it, and some of my other students have said this is really easy. So it shouldn't be something that's very daunting or hard. I think you're going to actually enjoy it too. When to graph frequency distributions using a bar graph, a histogram, or a polygon. Well, when we talked about those levels of data, the scales. Usually when we're talking about categorical data, we're going to use a bar graph. If we're talking about continuous data, then we're probably going to be using a histogram or a polygon, because we can actually get a midpoint. We can actually find out a midpoint in the data so that we can, have our equal intervals and that the categories don't have gaps in them. What normal, skewed, and bimodal distributions are, we're going to go over all that stuff. What relative frequency is? Well, how relevant is this group of data to the entire data? And I'll show you how to compute that. It's very easy. And then how to use the area under the normal curve. Well, basically, that is going to be what's called the Z distribution. The Z distribution is a normal distribution. It's the bell curve, the Gaussian curve, or it's called the Z curve. You'll get a Z score or a Z score, and we'll go over all that stuff, where Z is going to have a average or a mean of 0 and a standard deviation of 1. And we'll learn all that stuff in videos to come. Raw scores are scores that we initially measure in a study. So if I take a test, if I give you guys a test and then I collect all the scores and I write all the scores down, that's going to be raw data. I haven't done anything to that data yet. I haven't altered that data in any way. The number of times a score occurs in a set of data is called its frequency. So if I have several scores in the 70s, let's say I have 10 scores in the 70s, from 70 to 79, I will report that its frequency is 10. I have 10 scores in the C range. I have 8 scores in the B range and 10 scores in the A range, things like that. So I can actually make sense of the data. A frequency distribution organizes the scores based on each score's frequency, and it will actually give us a snapshot of what the distribution looks like. It can tell if it can tell us if the scores distribution are skewed, if they're normal, just by looking at it. It gives us a lot of information. And it's the total numbers of scores in a data set. Well, I didn't create this PowerPoint, and I think it's got a mistake in it, because they're using capital N for everything. And what I would like us to use is uppercase N and lowercase n, where uppercase N represents population data, and lowercase n represents sample data. Now in the PowerPoints you will see that uppercase n is used for both population and sample data, but we need to use the correct forms of n when we calculate population and sample data. Understanding frequency distributions. A frequency distribution table shows the number of times each score occurs in a set of data. And the symbol for the frequency is the lowercase italicized f. We're going to use this as an example here in just a few minutes. The following data, that's what raw data looks like. Let's say that I pulled off some quiz scores or something like that out of 20. And this is what the results were. So now I have to make sense of this data. I'll create what's called a frequency distribution and a frequency table. So that will tell me a lot about what the data looks like. Well, here we can see in table 2.1 that we have the scores and how many times those scores occurred, and we can see that n is equal to 18, and that tells us the total number of observations that we have. So we have 18 data points, and it looks like the score of 17 occurred one time. There was no 16s. 15 occurred 4 times, 14 occurred 6 times, 13 occurred 4 times, 12 occurred once, 11 occurred once, and 10 occurred once. So I can see that just by looking at this frequency here, the concentration of most of the numbers are going to be right in the middle here. A frequency distribution graph always shows the scores on the x-axis and their frequency on the y-axis. We talked about the x and the y-axis in the first video. Here we're going to see that again. Well, the type of measurement scale that we're going to use, nominal, ordinal, interval, or ratio, determines whether we use a bar graph, a histogram, or a polygon. And there's some other graphs out there, pie charts, ogives, things like that. But we're going to concentrate more on just the bar graph, the histogram, and the polygon, because that's what you're going to see most of the time in journal articles and magazines and television. Well, this is a typical bar graph. And as we can see here, we've got categories of Republicans, Democrats, I guess that's socialists, and communists. So what we're doing is we're taking categorical data, and this is going to be nominal level data because we're not rank ordering this. I'm not saying that Democrats are more important than Republicans and vice versa. So we're not providing rank order to this. All we're reporting on is these 4 categories and what their frequency are. So if we break this down, we can see the lowercase italicized f here. This is the frequency. And we could say that this is thousands of votes or something like this all over the world, or tens of thousands. So all over the world, we've got, it looks like 10,000 people prefer to be communists, and looks like 3,000 people socialists, Democrats, 8,000 per 100,000 or something like that, and Republicans 6,000 per 100,000. And it's up to you how you determine what this frequency is. You can break it down into different levels and things like that. So we'll need to put the frequency on this vertical scale, and remember always to put our data on the horizontal scale. Well, here we can see this is a histogram. So numbers of parking tickets. So numbers of parking tickets, that's probably going to be ratio because we're not looking at a minus number of parking tickets. So we've got our data it looks like it's actually connected here. Well, actually, that wouldn't be, we're still looking at a number of parking tickets. I can't break those down into, fractions. So, I'm still going to be looking at 0 point. You know, I've got an absolute 0 here. And for one parking ticket, you know, it occurred 9 times. So, people who only received one parking ticket, you know, that occurred 9 times, and it looks like people who only received 2 parking tickets, that occurred 7 times. People who received 3 parking tickets, that occurred 6 times. 4 parking tickets occurred 4 times. 5 parking tickets occurred 5 times. 6 parking tickets occurred 4 times. And 7 parking tickets occurred once. So only, you might say only one person out of a campus or something like that got 7 parking tickets, where 9 people on the campus received 1. So that's, and it gives you a good snapshot of what the data actually looks like too. Gives you a mental picture of it. This is what's called a normal curve. Well, with a normal curve, it is symmetrical, and symmetrical just means that this half is exactly the same as this half. If I folded this thing together, it would fold out and it has identical halves. So I have half of the observations over here and half over here. With, in this example, I've got 70 as the average. So basically, this looks like test scores or something like that. Very few, if we're looking at the frequency over here, very few received a 45. Only very few received a 95, with the bulk of everything occurring between 65 and 75. So this might have been a hard test. It might have been a calculus test or something like that. And we can actually break this down too, because we've got equal intervals here of 5. We can see that the amount of scores from 65 to 70 are the same as 55 to 65. The only difference is the frequency is occurring less often than it would at this increment between 65 and 70. Types of frequency distributions. Well, we just looked at a bell-shaped curve, and that's what's called the normal curve or the Z-curve. There it is, normal distribution. It is symmetrical. The far left and right portions containing the low frequency of scores, that is going to be called the tails. The tails do not touch on a frequency distribution such as this because they go on for infinity. We don't know what those scales are, or we don't know what those scores are. We don't know what the end of the normal curve is on both ends. It's open for interpretation. It goes on and on. And as you can see, there is no closure to the tails. They are left open, so this, as you can see these dots, it will go on for infinity. However, we do provide parameters to these, but as far as the actual distribution goes, it goes on forever. This particular curve, we've got 30 as a mean or an average, and we've got 20, or basically 5 increments here that we've broken this thing down into, and we'll get into more of that as the semester goes on as well. But this is just a good way to look at the data, with most of the data occurring between 25 and 35. Skewed distributions. One thing about skewed distributions are that the data is not symmetrical. The data has extreme scores to either the low side or the high side, the negative side or the positive side. It has only one pronounced tail. You can see it. The easy way to recognize a skewed distribution is if it has an elongated tail. That means there's extreme scores pulling that distribution either to the left or to the right. Now, the direction of skewness depends on which way the tail is pointing. So I like to grill. I have skewers at home. and I put the skewers into the meat and the vegetables and put them on the grill. Well, the skewer has a pointy end to it, and whichever end I point that thing to, just think of that as a direction of skewness. If the pointy end is pointing to the right, then basically I have what's called a positively skewed distribution. If the pointy end is actually pointing to the left or the negative side of the distribution, I will have a negatively skewed distribution. And here we go. The long end over here is basically pulling this distribution to the negative side. So think of this as that skewer. It's over here to the left, so this would be negatively skewed. It contains extreme low scores having low frequency, but does not contain low frequency at the high side. So you're not going to see very low scores over here in the high side. You're going to see them over here with the bulk of it being, at the high side. But you have extreme scores pulling it into a skewed shape. A positively skewed distribution is doing the same thing, only you're going to have extreme scores to the high side instead of the low side. This contains extreme high scores having low frequency, but does not contain low frequency, extreme low scores. You're not going to have them, way over here, but you will have extreme scores to the high side. That would make it positively skewed. Income is an example of this. If I have income that is normal, so if there is normal income in, let's say, Okmulgee, and normal income or the average income is $45,000 for a household of 4, and some rich people, like billionaires, move into Okmulgee, that's actually going to skew the distribution of income to the positive side, because these people might be making, billions of dollars per year instead of, like $50,000 a year. And it's actually going to distort the shape of the distribution, and it's going to skew it to the positive side. Bimodal distribution. The mode is the most frequently occurring number in a data set. Sometimes we have 2 or 3 modes. This would be a bimodal, and if you have more than 2 modes, then you're going to have what's called a multimodal distribution. But this, we always think of this as the camel's back, and it has more than 1 mode, and a lot of distributions do have more than 1 mode. Relative frequency. Well, relative frequency is just basically frequency over the number of observations in a data set. We want to know how relevant a particular number is to the rest of the data. And by dividing frequency over the observations, we can get a percentage of frequency, how relative that is in percentage. So if we have 18 observations and you have a number up here, you just divide that to find out what percentage you have, and that would be your relative frequency. Relative frequency, basically this is normal, so I can take 25 here, and I can add all these 25s up, and then I can take 25 and find out how relative that is to all the rest of the dots. But I got to know what the number is of all the dots in this distribution, and I don't want to take that time right now to do that. But we're going to do some examples of that. Understanding percentiles. Well, a percentile is basically a score that falls at or below a score. So if you say that your child is at the 50th percentile in his weight group, basically that means he's at or below 50% of all the other kids in his weight group. So he's average, so that's a good thing. One way to determine the score's percentile is to use the area under the normal curve. So we have a normal curve, and then we have areas that you can basically calculate what a percentile would be. And it's pretty easy once we understand what those areas are under the normal curve. The percentile for a given score is a percent of the score below it. Equal to it, and that's how basically you would report that, at or below a certain score. The percent of the normal curve to the left of the score. So that's what's going to be below it. So if you had a test score, an ACT score, something like that, and you got a percentile rank of 90, that means you're at or below only 10%, and which is very good. That means only 10% of your peer group scored higher than you did on the ACT. And here's a picture of this. The 50th percentile will be, the mean here, of course, the median. And then if you scored at 20, that's only 15% of the curve, and like say 85, and then you had 90, 95. So it just depends on where you would fall, and then you can find out what your percentile rank is. Another data set, we want to find out what the relative frequency of 12 is. So what you'd have to do is find out how many times 12 occurs in this data set, and it looks like it only occurs once. So what we'd have to do is we would take 1 out of, it looks like 18, and we would divide that. So 12 occurred one time over 18, so we would actually try to find that relative frequency, and it looks like when we do the math on this, we come out with a value of 0.06, or 6% of the whole data set. So 12 has a relative frequency of 6% of the total data set. And that's it for now.